Welcome to Science, to Sleep By. Tonight, we uncover why NASA quietly reactivated a secret surveillance system called 3i Atlas, a move meant to solve one of America's most urgent, invisible problems, protecting our planet from what we don't yet understand coming from deep space. The night sky above the United States has always held more than just stars. It's a vast, silent ocean of mysteries, and every now and then, something stirs beneath its surface, something unexpected. On this particular day, NASA did something quietly, something not broadcasted in the usual fanfare of press releases or celebratory social media posts. Deep within the operational corridors of its surveillance network, a classified protocol labeled 3i Atlas was officially reactivated. To the public, this might sound like just another technical adjustment, another line in an internal log. But to those who understand the language of space observation, this single move signals the awakening of a sleeping guardian. This hidden activation wasn't meant to draw eyes. It was designed to move beneath the radar, a coordinated switch on of instruments across several observatories under NASA's expanding planetary defense network. The reason for the secrecy lies in the nature of the mission itself. The Atlas system, short for Asteroid Terrestrial Impact Last Alert System, was originally created to detect near-Earth objects that could potentially collide with our planet. But the recent internal documents, coded under the name 3i, suggest that something different may have triggered this particular response. In scientific terminology, the designation 3i refers to the third interstellar object ever detected entering our solar system. The first, 1i Oumuamua, passed silently through the solar system in 2017, leaving scientists baffled by its cigar-like shape and strange acceleration. The second, 2i Borisov, was a more traditional comet, icy, tail-bearing, and slightly easier to explain. But 3i, whatever it truly is, represents something else entirely, something that demanded NASA to turn back on a dormant part of its cosmic surveillance infrastructure. This quiet activation hints that a new visitor, possibly an object from beyond our solar neighborhood, has been spotted again. Imagine for a moment the atmosphere within NASA's Jet Propulsion Laboratory or the Minor Planet Center when data began to appear, faint streaks across telescope arrays in Hawaii, Chile, and Arizona. At first, the signals may have been dismissed as noise, a false detection, or a cosmic ray interfering with the CCD sensors. But as the same streak began to align across multiple instruments, the probability of coincidence collapsed. Something was moving fast, unfamiliar, and most importantly, not gravitationally bound to the sun in the way typical comets are. Its orbit didn't close. It cut through. That single fact was enough to trigger the internal chain of communication that culminated in a single action: activate Atlas. For decades, the United States has invested heavily in monitoring the heavens. Most of this effort has been public educational programs, open data, and citizen science projects. But beneath that openness lies a structured system of classified monitoring operations that form the country's Planetary Defense Coordination Office, PDCO, a joint effort between NASA, the Department of Defense, and select research universities. Its goal is straightforward but daunting: detect and track anything that could endanger Earth from above. The activation of 3i Atlas, however, wasn't about something that threatens Earth directly, at least not yet. It was about uncertainty. Uncertainty is the most dangerous thing in space science. We can measure trajectories, predict orbits, and calculate energy yields of potential impacts. But when something doesn't behave according to the models, it introduces what researchers call a non-gravitational anomaly. 1i Oumuamua was one such anomaly, accelerating as if propelled by invisible forces, with no visible gas or dust emission. That event unsettled astrophysicists, not because it posed a risk, but because it didn't fit any known pattern. So when data appeared suggesting another interstellar object might be approaching, the quiet alarm bells began to ring. NASA's response was measured but swift. The order to reactivate Atlas wasn't a declaration of emergency, it was a signal of vigilance. The system, when fully active, connects observatories across the world to constantly sweep the night sky for faint moving points of light. Each detection is analyzed, compared, and triangulated to determine whether it belongs to a known catalog object or a potential new arrival. With 3I Atlas active, the detection range effectively expands beyond the usual near-Earth limits, allowing observation of deeper sky regions where interstellar objects could emerge. For the American public, such movements often remain invisible. There are no breaking news alerts, no live streams from mission control. But inside the quiet laboratories of space science, researchers are aware that such actions mark moments of historical potential. If indeed this is another interstellar object, it means once again humanity has the chance to study a fragment from another star system, a messenger carrying chemical and structural clues about how planets form in environments vastly different from our own. However, the term secret in this context doesn't necessarily imply deception or concealment from the public for sinister reasons. In scientific operations, secrecy can be a shield for accuracy, preventing premature conclusions, protecting the integrity of data, and avoiding misinformation. NASA, by nature, must balance transparency with caution, especially when new cosmic discoveries intersect with national interest or potential geopolitical implications. If an interstellar object's trajectory crosses near Earth's orbital path, even slightly, it could demand coordination with defense agencies to model potential scenarios. Thus, the word activation in 3I Atlas is as much about readiness as it is about research. The United States has learned from past experiences how critical readiness can be. The Chelyabinsk meteor in 2013, which exploded over Russia and injured over 1,000 people, was undetected until it entered the atmosphere. That event was a global wake-up call, reminding governments that cosmic threats are neither fictional or distant. Since then, NASA's planetary defense programs have evolved from theoretical exercises into real-time operations, incorporating machine learning algorithms, automated telescopic arrays, and global data sharing agreements. 3I Atlas represents the next step in that evolution, a more sensitive, interconnected web designed to detect the unpredicted. There's also a deeper layer to this activation, the psychological one. Human beings are drawn to the unknown, but they also fear it. The idea that something from beyond our solar system could drift through our neighborhood evokes both wonder and unease. NASA understands this balance. It must communicate discoveries with awe, not alarm. And yet, there's a quiet understanding among those who work in the field. Every interstellar visitor is a reminder of how little we truly know about the cosmic environment around us. The activation of 3I Atlas, therefore, isn't just a technical event, it's a philosophical moment. Somewhere between secrecy and discovery, between fear and curiosity, the system hums to life, scanning the sky for a speck of moving light that could carry answers to questions humanity has been asking since it first looked upward. What lies beyond our solar system? How many of these travelers pass us by unnoticed? And perhaps most intriguingly, what if one day, one of them didn't just pass through? In the heart of NASA's control rooms, amidst the quiet hum of computers and the soft glow of monitors, that's the question that lingers. Scientists lean closer to their screens, not in panic, but in fascination, as they watch the data streams populate numbers, coordinates, magnitudes, velocities. Somewhere among those figures could lie the first whispers of 3I, the next interstellar object, the next clue in our unfolding understanding of the universe. And as the Atlas network reawakens, the watchers of the sky ready themselves once again for what it might reveal in a world where humanity's attention is consumed by terrestrial issues, politics, climate change, and technological competition. There exists an ever-present, but rarely discussed vulnerability above our atmosphere. It's a vulnerability that doesn't conform to national borders or political divisions, yet it has the power to reshape the course of human civilization within seconds. This vulnerability comes not from an enemy nation or a hostile power, but from the cosmos itself. It's the persistent risk posed by near-Earth objects, or NEOs, asteroids, comets, and interstellar debris that drift through a region of space, sometimes without warning. For the United States, a nation that relies heavily on infrastructure, satellites, and global communication networks, the threat of a celestial impact isn't a science fiction scenario, it's a national security concern disguised as an astronomical curiosity. The problem begins with scale. The Earth is constantly bombarded by small meteoroids, grains of dust and rock that burn up harmlessly in the atmosphere. They create shooting stars, those brief flashes that paint the night sky. But for every harmless meteor, there exists a population of larger bodies, hundreds of meters across, that could unleash energy equivalent to millions of tons of TNT if they struck the planet. Some of these are known, carefully tracked, and cataloged. But others, perhaps most of them, remain unseen, drifting through the void. The limitations of current detection systems mean that a large object could approach Earth from a direction hidden by the sun or from deep space. Giving humanity little to no warning, the United States has invested billions of dollars into space-based observation. But the truth is that our planet's defense against cosmic threats remains far from complete. The Asteroid Terrestrial Impact Last Alert System ATLAS, operated by NASA and the University of Hawaii, was designed to detect smaller asteroids days or weeks before they might impact Earth. While it has succeeded in identifying several potential impactors, it is not infallible. The detection range is constrained by light sensitivity and viewing angles. When an object is too dark, too small, or approaching from an angle that ground-based telescopes can't see, it can slip through unnoticed. The activation of 3i ATLAS suggests an attempt to close that gap, a recognition that new threats may not fit neatly within our existing models of observation. This problem extends beyond technology. It's also strategic and psychological. For decades, planetary defense has existed on the fringes of mainstream science and policy, often regarded as speculative or distant. Yet, as recent discoveries show, interstellar objects like Oumuamua and Borisov can enter our solar system unexpectedly, moving at speeds and trajectories that defy easy prediction. Each of these cosmic visitors represents a reminder that our solar system is not isolated. There are highways of interstellar debris crossing through it, pathways carved by gravitational currents from nearby stars. Any object traveling on these trajectories could theoretically pass near Earth. The challenge for NASA and the U.S. defense community is that these encounters are nearly impossible to forecast without constant, high-resolution monitoring of the sky. The United States faces a unique pressure in this domain because of its leadership role in space science. As the hub of the world's most advanced astronomical instruments and defense technology, the U.S. carries an unspoken responsibility to act as Earth's early warning system. Other nations rely on NASA's data, its alerts, and its rapid analysis of potential threats. But that leadership comes with the expectation of perfection, an expectation that's nearly impossible to meet given the sheer scale of the problem. The reactivation of ATLAS, then, isn't just about scientific curiosity. It's about maintaining credibility in a world where even one missed detection could have global consequences. The physics of impact are unforgiving. Even an object just a few dozen meters wide can cause devastation on a continental scale. In 1908, the Tunguska event leveled over 2,000 square kilometers of Siberian forest. Scientists estimate the object responsible was only 50–60 meters in diameter. The Chelyabinsk meteor in 2013, just 20 meters wide, released energy equivalent to nearly 500 kilotons of TNT, enough to shatter windows in 6 cities and send shockwaves felt across the region. Both of these events occurred without warning. If either had exploded over a populated region in the United States, the results would have been catastrophic, not only in human loss, but in economic disruption and political fallout. In a country where entire sectors depend on satellite networks and power grids, even a near miss could cause cascading effects. There's also the question of cosmic invisibility, the fact that some objects, particularly interstellar ones, may not reflect light in ways our current sensors can easily detect. Interstellar visitors can be dark, fast, and non-reflective, moving on orbits that cut sharply through the solar plane. Their detection often depends on luck, on whether a telescope happens to be scanning the right patch of sky at the right moment. The Atlas system was designed to provide humanity with a last alert, a few days of warning before an impact. But for interstellar objects moving at tens of kilometers per second, even that window might close before detection. That is the vulnerability NASA's new activation aims to address. Beyond the immediate threat of impact lies a subtler problem: knowledge gaps. Humanity still knows astonishingly little about the composition of these cosmic travelers. Are they icy bodies shedding vapor as they near the sun, or metallic fragments of shattered worlds? Could they carry organic molecules, or do they represent material from dead stars, dense and alien in nature? The inability to answer these questions means that when one approaches, scientists cannot always predict its behavior. Some may break apart before reaching Earth's atmosphere. Others may accelerate unpredictably, influenced by outgassing or internal magnetic fields. Without understanding, there can be no reliable modeling. Without modeling, there can be no defense. For the United States, the stakes are more than scientific, they're existential. The interconnected systems that power modern life are vulnerable to disruption not just from space impacts, but from the secondary effects that such events can cause. A mid-sized impact in the ocean could generate tsunamis. An airburst could ignite wildfires. Even the atmospheric dust from a moderate strike could alter weather patterns temporarily. The U.S., as a major global power, cannot afford to be reactive in such scenarios. Preparedness must be proactive. Thus, when NASA reactivates a surveillance network like 3i Atlas, it isn't merely scanning for rocks, it's asserting a form of planetary stewardship, one rooted in the belief that knowing first means surviving best. This reactivation also reflects the evolving relationship between science and defense. What once belonged solely to astronomers has now become a collaborative field involving data scientists, aerospace engineers, and national security analysts. The Department of Defense monitors space for human-made threats like satellites and missiles, but increasingly, it must also consider natural cosmic events. A large enough asteroid could mimic a missile signature upon atmospheric entry, potentially triggering confusion or even geopolitical tension if not properly identified. NASA's activation of a specialized network like 3i Atlas ensures that such ambiguities can be resolved with precision and speed, maintaining stability in both the scientific and military realms. Yet the greatest challenge remains awareness. Most of the American public rarely considers the possibility of an extraterrestrial impact. It's not a daily concern, and perhaps it shouldn't be. But the quiet truth is that the cosmos doesn't operate on human timelines. Objects on million-year orbits can intersect with Earth's path tomorrow, not because of destiny, but because of the statistical inevitability of celestial motion. NASA's scientists, armed with probability models and deep space sensors, understand this better than anyone. To them, planetary defense isn't a speculative exercise, it's the logical continuation of the same instinct that drives humanity to build levees against floods, shelters against storms, and vaccines against invisible pathogens. It's about preparation for the improbable. Because the improbable has always been what tests civilization the hardest. So, when NASA chooses to reactivate a system like 3i Atlas, it's not responding to hysteria, it's responding to math. The equations that describe orbital mechanics and impact probabilities don't rest. They run continuously, whispering through data streams, reminding humanity that vigilance must be constant. Every observation, every update to the sky map, is another line of defense in a war without an enemy. Only objects, silent and indifferent, passing through the darkness of space. The discovery of 3i Atlas began not with a dramatic announcement or a burst of public excitement, but with a faint anomaly, a small, fast-moving streak of light recorded by a telescope in the early hours of a quiet morning. In astronomy, most discoveries do not start with certainty. They start with confusion. Observers at one of the Atlas survey stations in Hawaii noticed a data inconsistency. A moving point of light appeared in successive images, crossing the field at a velocity that immediately seemed unnatural for any ordinary comet or asteroid native to our solar system. The object's speed exceeded the sun's gravitational limit for bound motion, suggesting it wasn't looping through the solar system, but slicing through it. For the scientists reviewing the data, the first instinct was to verify. Automated detection algorithms can mistake satellite glints, cosmic rays, or even atmospheric distortions for real objects. The image was sent for cross-analysis with data from other observatories within NASA's network. Within hours, telescopes in Chile, Arizona, and South Africa were scanning the same region of sky. They confirmed what the initial detection suggested: the object was real, and its velocity, approximately 45 kilometers per second relative to the sun, was consistent with something entering from interstellar space. In astronomical terms, that made it historic. Objects like this are assigned a formal classification upon verification. The prefix I stands for interstellar, marking it as a visitor from beyond the solar system. The first such object, one Iuma, startled the scientific community in 2017 when it defied categorization. It was not a comet, yet it accelerated as if it were being pushed by outgassing. 2 years later came 2I Borisov, a much more traditional comet, with a visible tail and clear chemical signatures of ice and dust. The appearance of a third such object, 3I Atlas, marks not an isolated event, but a pattern. The cosmos, it seems, is not a sealed system. Objects from other star systems cross into ours more frequently than once believed, traveling as silent emissaries from distant worlds. The discovery was made possible because of the Atlas system's unique sensitivity to rapid movement across the sky. Each of its telescopes scans the entire visible dome several times a night, looking for transient events, flashes, streaks, and moving points. It's a watchful network, designed primarily for planetary defense, but its design also makes it a perfect tool for identifying fast, unpredictable interstellar visitors. When the system flagged the object, an automatic alert was generated. However, given the object's speed and trajectory, NASA scientists decided not to immediately publish its detection in the Minor Planet Electronic Circulars, as they normally would. Instead, internal channels were activated under the designation 3I Atlas, a title reflecting both its discovery source and its extraordinary nature. The discovery wasn't simply about location or speed. It was about trajectory. Unlike normal asteroids, which orbit within the plane of the solar system, 3I Atlas entered at a sharp inclination nearly 40 degrees relative to the ecliptic plane. Its hyperbolic path suggested an origin far beyond the gravitational influence of any known planetary system near ours. Simulations run through NASA's Jet Propulsion Laboratory indicated that its vector could trace back toward a region near the constellation Lyra, though the uncertainty was vast. The cosmos, with its countless gravitational influences, can bend the paths of small bodies like threads in an invisible tapestry, making it nearly impossible to pinpoint their exact birthplace. Early spectral analysis of 3I Atlas showed something intriguing. Its reflected light was faint and reddish, similar to organic-rich asteroids known as D-type. These bodies are believed to be composed of carbon compounds, possibly formed in the colder regions of protoplanetary disks. Such a composition suggests that 3I Atlas could be carrying material formed under conditions completely different from those of our own solar system, perhaps around a red dwarf star or in the outskirts of an ancient stellar nursery. For scientists, that single piece of evidence transforms a small dot of light into a potential time capsule, a fragment of another world's beginning. The activation of the Atlas system under the 3I designation meant that telescopes across multiple continents and orbital observatories began tracking the object simultaneously. Each new measurement refined its path and its physical characteristics. Observations from NASA's infrared survey satellites suggested that it was relatively small, no more than a few hundred meters across, but unusually dense. Its light curve fluctuated erratically, implying an irregular, possibly tumbling shape, much like one Iuma. This irregularity posed challenges for measurement, but it also hinted at a violent past. Objects that tumble often do so because of collisions or fragmentation events, perhaps remnants of an ancient planetary system shattered by gravitational forces. For the scientists involved, the emotional tone of discovery is a complex mix of awe and urgency. Each new interstellar object is a fleeting opportunity. These bodies move fast, and once they pass their closest approach to the sun, they fade into the outer darkness, becoming unreachable. The window for observation is measured not in years, but in weeks. NASA's teams knew this. As data poured in, coordination with international observatories intensified. The European Space Agency, Japan's JAXA, and independent research groups across the world began pooling information, while NASA's Planetary Defense Coordination Office quietly elevated its alert status, not because of any direct danger, but because every new discovery of this nature requires verification under strict protocols. The discovery of 3I Atlas also reignited scientific debate about the frequency and origin of interstellar objects. Before Oumuamua, astronomers believed such encounters would be extraordinarily rare, perhaps once every 100,000 years. Now, with 3 detections within less than a decade, the question shifted. Were these objects always there, and humanity had only just built the instruments capable of noticing them? Or was something changing, some gravitational or galactic phenomenon increasing the number of interstellar fragments entering our region of space? The possibility that these objects represent the cosmic debris of distant stellar disruptions adds another layer of significance to their detection. In the background of this discovery, the language of secrecy began to intertwine with the language of science. When NASA activated Atlas under the 3I designation, the communication was internal and coded. The reasoning was simple: early data on interstellar objects can easily be misinterpreted, and premature public announcements risked fueling misinformation. But in the digital age, even quiet data movements attract attention. Amateur astronomers scanning NASA's open databases noticed unusual patterns, datasets that had suddenly become restricted, observation logs missing from the usual nightly uploads. Speculation began to spread across online astronomy forums. Some suspected that NASA had found something unusual, something beyond a mere rock. Others assumed it was simply another fragment of interstellar debris. In truth, no one outside the official channels knew for certain. Meanwhile, within NASA's research divisions, teams worked to model the object's composition using reflectance spectroscopy. The results were puzzling. The surface appeared to be coated in a layer of material that absorbed most wavelengths of light, suggesting either a carbon-rich compound or an external crust formed through cosmic radiation exposure over millions of years. This outer layer could mean the object had been traveling through interstellar space for an immense period of time, bombarded by charged particles that darkened and hardened its exterior. Some scientists hypothesized that beneath this layer could lie pristine material unchanged since the early formation of its original star system. The implications of such a discovery are profound. Each interstellar object offers a chance to test theories about how solar systems evolve, how planets form, and how elements necessary for life are distributed across the galaxy. If 3I Atlas contains organic molecules or complex carbon structures, it could provide clues about whether the ingredients of life are universal, scattered freely among the stars. Even the absence of such materials would carry meaning, helping to define the boundaries of cosmic chemistry. Yet, despite its potential, the discovery of 3I Atlas remained cloaked in quiet. NASA scientists understood the rarity of the event, but also its limitations. The object was moving fast for any current spacecraft to reach or intercept. Proposals for future missions, like rapid response probes capable of chasing interstellar visitors, suddenly gained new urgency. 3I Atlas was a reminder that space is not static. It is alive with motion, with encounters and departures that happen beyond our notice. The official acknowledgement of 3I Atlas, when it eventually appeared in the astronomical record, would read as a few simple lines of coordinates, brightness measurements, and velocity data. To the public, it might look ordinary, but for those who understand the language of those numbers, it represents a moment of profound significance, the brief crossing of two worlds, the reminder that our solar system is not isolated, and that somewhere in the darkness beyond, other systems are sending their fragments our ways endlessly, as the cosmos continues its quiet exchange of matter and mystery. When the internal order for NASA's secret activation of 3I Atlas was issued, there were no press releases, no social media updates, and no formal statements. It was a silent event, hidden beneath layers of operational coding and technical language that few outside of specific departments could interpret. Yet within NASA's network, the activation was unmistakable. It began as a series of encrypted transmissions sent from the Planetary Defense Coordination Office in Washington, D.C., to a list of observatories and partner institutions spread across the United States and abroad. The language was procedural, but the timing was telling. A dormant segment of NASA's sky monitoring infrastructure was coming back online, not for a scheduled test, but for a purpose that demanded immediate readiness. This secret activation was never meant to be secret in the conspiratorial sense. Rather, it reflected the culture of controlled communication that governs high-stakes scientific events. Whenever a detection or signal could potentially lead to widespread public speculation or misunderstanding, NASA proceeds carefully. The decision to quietly bring 3I Atlas online represented both caution and urgency. The agency needed full clarity before it could risk public interpretation. The same pattern had occurred in 2017, when the strange behavior of one Oumuamua triggered a flood of hypotheses, from natural comet theories to claims of artificial origin. This time, NASA intended to proceed differently. The activation process itself was complex. ATLAS, or the Asteroid Terrestrial Impact Last Alert System, is not a single telescope, but a distributed network of automated observatories capable of sweeping the entire visible sky several times each night. Before the activation, several nodes of this network had been operating in limited capacity, prioritizing near-Earth object searches. The 3I protocol required a new configuration and extension of scanning range, recalibration of optical sensitivity, and the synchronization of data streams with other NASA and Department of Defense instruments. Every telescope in the network was instructed to adopt a new tracking algorithm optimized for hyperbolic trajectories, those paths characteristic of interstellar objects moving too fast to be bound by the sun's gravity. Behind the technical maneuvers lay a deeper coordination effort. The activation message traveled beyond NASA, reaching institutions like the U.S. Space Surveillance Network, the National Optical Infrared Astronomy Research Laboratory NOIRLab, and selected facilities within the European Southern Observatory. Even though the program carried NASA's name, its reach extended across multiple agencies and nations. A silent web of astronomers, data engineers, and defense analysts began their synchronized watch. While much of NASA's work is public, these moments of covert coordination are essential when signals need to be verified beyond any doubt. Inside NASA's Mission Operations Center, screens lit up as the new parameters were applied. The data flow doubled. Observers watched as millions of points of light passed through the algorithm's most routine, some flagged for review. Each new observation was cross-referenced against the Minor Planet Center database to eliminate known asteroids. Anything unrecognized, any motion that matched the expected speed and direction of an interstellar trajectory, was tagged with higher priority. Within hours of the activation, the system had produced its first series of confirmed observations of 3I Atlas. The word activation in NASA's internal vocabulary carries a specific weight. It indicates a state of operational readiness, a transition from observation to analysis, from passive to proactive. The reactivation of Atlas under the 3I designation meant that all available computational and optical assets were to prioritize tracking and characterization. That included not only ground-based telescopes, but also orbiting observatories capable of infrared and ultraviolet imaging. Infrared readings are particularly crucial for understanding the thermal properties of fast-moving objects, whether they're icy, metallic, or coated in organic compounds. When the data from these sensors began to flow, the team realized why the program needed secrecy. The thermal readings did not conform to typical cometary models. The object appeared to retain heat unevenly, as if composed of materials with different densities and reflectivities. This deviation didn't immediately imply danger, but it did imply mystery. NASA's scientists had to proceed under controlled silence until more information could be verified. The secret activation ensured that speculation would not precede science. In a world saturated by instant communication, even a small anomaly can ignite waves of misinformation before experts can provide context. The agency had learned from previous events that the line between scientific discovery and public panic can be very thin, especially when the words unknown and space object appear in the same sentence. To maintain security and accuracy, NASA implemented compartmentalization protocols. Only specific teams were granted access to raw data. Analysts were tasked with cleaning and verifying images before any were transmitted to wider research databases. The program was classified at a restricted dissemination level, meaning its existence wasn't concealed, but its operational details were. Internally, the reactivation of Atlas was recorded as a planetary defense exercise, though all participants knew it was far more than a simulation. It was a test of preparedness under live conditions, a rehearsal for the next phase of humanity's growing role as guardian of its own planet. The activation also represented a shift in NASA's operational philosophy. Historically, the agency has functioned as a purely scientific institution dedicated to exploration and understanding. But with the rise of planetary defense initiatives, its mandate has expanded. The cosmos, once viewed solely as a realm of discovery, is now also seen as a frontier of potential hazard. The activation of 3I Atlas demonstrated that NASA is no longer observing the universe passively, it is watching it strategically, anticipating threats and coordinating responses in real time. Within the days following activation, the Atlas system's feed was integrated into machine learning-driven data analysis tools. These algorithms could identify faint, fast-moving signals that human observers might overlook. NASA's Artificial Intelligence Laboratory, working under the Applied Sciences Division, modified its predictive model to include interstellar velocity profiles derived from past detections. The software was instructed to search for similar signatures that might indicate other, smaller fragments traveling in association with 3I Atlas. The possibility of fragmented interstellar streams had been proposed by astrophysicists after Oumuamu's detection, suggesting that interstellar objects could arrive not as isolated travelers, but as remnants of larger, disintegrated bodies. As data continued to flow, NASA's scientists began to notice faint traces that hinted at additional objects, smaller, dimmer, perhaps related. The activation of Atlas had achieved its purpose. It revealed what static observation had missed. The universe, once thought to be empty between stars, appeared to contain a far greater number of wandering fragments than previously imagined. The secret program wasn't only about a single detection. It was about testing a broader surveillance architecture for cosmic phenomena that humanity was only beginning to understand. Throughout NASA's history, certain programs have operated quietly, parallel to the public missions that inspire the world's imagination. Apollo had classified engineering tests. The space shuttle era had hidden defense payloads. But 3I Atlas was different. It wasn't about national defense in the traditional sense, but planetary continuity. Its secrecy was born not from military need, but from scientific responsibility. The world is not yet prepared to handle the uncertainty that comes with interstellar discovery, especially when such findings hint at phenomena outside of the ordinary models of astrophysics. Meanwhile, in research centers across the country, select astrophysicists received encrypted access to portions of the data. Many worked late into the night, reconstructing the object's path using orbital dynamics equations. Every calculation seemed to confirm the same conclusion: 3i Atlas was on a hyperbolic course that would carry it through the inner solar system and back into interstellar space, never to return. That trajectory placed its closest approach somewhere beyond Mars, meaning it posed no immediate risk to Earth. Still, the secrecy remained. The object's irregular motion and unexpected heat distribution suggested that its behavior might change as it interacted with the sun's radiation and magnetic fields. NASA couldn't assume stability until more observations were gathered. Within NASA's internal archives, the activation of 3i Atlas became a case study in quiet coordination. Teams across multiple continents worked in synchronization, unified by a shared understanding of what was at stake. The activation wasn't just a technical process, it was a test of trust, timing, and the global infrastructure of space vigilance. Scientists from rival nations exchanged data through encrypted channels, bound by the mutual recognition that in the face of cosmic phenomena, cooperation outweighs competition. The universe doesn't respect borders, and neither do the objects that move through it. The data from 3i Atlas would later form part of a classified report circulated through NASA's upper echelons and the U.S. Department of Defense. The document summarized the success of the activation and the object's characteristics, but it also raised deeper questions. If interstellar objects are this frequent, how many have passed undetected? How many more will arrive within the next decade? And what unknown factors might they introduce, biological, chemical, or energetic? For now, these questions remain open, quietly echoing through the halls of research institutions as NASA's telescopes continue their watch, guided by a network that was never meant to sleep. To understand the full significance of NASA's activation of 3i Atlas, it's essential to step into the scientific context that gives weight to the event. The universe, vast and unending, not an empty stage, but a theater of constant motion. Stars are born, planets form, and debris, ancient fragments of those processes, drift endlessly through interstellar space. Most of what humanity knows about the cosmos comes from studying its light, but light alone cannot capture the full complexity of the material universe. That's where interstellar objects, like 3i Atlas, come into play. They are not distant signals. They are physical messengers, pieces of other solar systems that find their way into ours. Every such object carries a history older than humanity itself, etched in the atoms that compose it. The scientific context behind 3i Atlas begins with its classification. The I designation marks it as interstellar, meaning it does not belong to the gravitational family of the Sun, unlike comets and asteroids that loop around the Sun on predictable orbits. Interstellar objects travel in hyperbolic trajectories. They enter, they pass through, and they leave. Their speed exceeds the Sun's escape velocity, ensuring they will never return once they depart. This makes them rare and precious to science. Each encounter represents a fleeting chance to study material formed in another star system, untouched by the billions of years of solar radiation and gravitational influence that shape the objects native to our own system. When astronomers first detected 1i Oumuamua, the scientific community was astonished by its physical characteristics. It lacked a visible coma or tail, features that typically define comets, yet it accelerated slightly as though some force were pushing it. This defied the conventional understanding of celestial mechanics. Later, when 2i Borisov was discovered, it appeared far more conventional, a comet with familiar outgassing behavior and composition. Between these two extremes, the scientific spectrum of interstellar bodies began to form. Now, with 3i Atlas, scientists find themselves standing at the threshold of the unknown again, faced with an object that seems to combine the unpredictability of Oumuamua with the recognizable properties of Borisov. The study of interstellar objects operates at the intersection of astronomy, astrophysics, chemistry, and planetary science. Each detection prompts a cascade of questions. Where did it come from? How old is it? What does it tell us about the formation of planetary systems elsewhere in the galaxy? These questions are not abstract, they are central to understanding our own cosmic origins. Every interstellar object offers a chance to test the idea that the materials and conditions that led to life on Earth might exist elsewhere, scattered across the galaxy. NASA's scientific interest in 3I Atlas extends beyond curiosity. It lies in the physics of how such objects travel through space. When an interstellar body moves between stars, it experiences a journey unlike anything within our solar system. It passes through regions filled with magnetic fields, cosmic radiation, and interstellar gas clouds. Over millions or even billions of years, its surface chemistry transforms. Radiation alters its molecules, darkening them and producing complex organic residues. Scientists call this space weathering, and it acts like a chronicle of time, a record of exposure written in carbon, hydrogen, and oxygen. Studying 3I Atlas could therefore help scientists decipher the chemical fingerprints of distant worlds. The problem, however, lies in observation. Interstellar objects move at extraordinary speeds, sometimes faster than 100,000 miles per hour. By the time they are discovered, they are already passing through the inner solar system, giving astronomers only weeks to gather data before the object fades into the outer darkness. The challenge is compounded by their dimness. Because many are small and reflect little sunlight, detecting them requires telescopes with high sensitivity and sophisticated tracking systems capable of compensating for their unusual velocities. This is why the reactivation of Atlas under the 3I designation was so crucial. It represented the culmination of years of preparation to capture an event that could last only moments in astronomical time. The scientific instruments used to study such an object operate across multiple wavelengths. Optical telescopes provide images of brightness and motion. Infrared sensors measure the heat the object emits, revealing clues about its composition and surface texture. Spectrographs split the light from the object into its component colors, allowing scientists to identify the presence of specific elements or compounds: carbon, silicates, metals, ices. Each dataset contributes to a growing mosaic of information that helps define what 3I Atlas is made of and how it behaves. Preliminary readings from Atlas and other telescopes suggested that 3I Atlas had a red-tinted spectral signature, similar to certain carbon-rich asteroids and distant Kuiper belt objects. This reddish hue indicates the presence of Tholen's complex organic molecules formed by ultraviolet radiation acting on simpler compounds like methane and ammonia. On Earth, such molecules are rare, but in the outer reaches of planetary systems, they are common, hinting at the universality of organic chemistry. If 3I Atlas indeed carries tholins or related materials, it would be evidence that organic matter is not unique to our solar system, but widespread, a natural byproduct of cosmic processes occurring across the galaxy. The physics of its motion adds another layer of intrigue. Calculations show that 3I Atlas is traveling on a hyperbolic orbit with an eccentricity greater than 1, confirming its interstellar origin. Yet its path isn't smooth. It displays subtle variations in velocity and orientation, possibly due to asymmetric heating as sunlight strikes its uneven surface. This same behavior was observed with Oumuamua, whose acceleration puzzled scientists for months. In both cases, traditional explanations like outgassing, a process where sublimating ice produces thrust, don't fully account for the observed dynamics. That discrepancy raises profound questions about how interstellar bodies interact with stellar radiation, suggesting that our understanding of these processes remains incomplete. There's also the matter of origin. By tracing 3I Atlas's trajectory backward through time using models of galactic motion, astronomers can approximate the region of space from which it came. Early simulations suggest its path may have originated in a dense region of the galactic disk, possibly from a stellar nursery or an aging star system where gravitational disturbances ejected it long ago. This ejection process is thought to occur frequently when young stars form planets. Gravitational interactions can fling smaller bodies into interstellar space, turning them into wanderers. Each of these fragments becomes a carrier of information, a messenger from a system that might once have resembled our own. NASA's scientists approach these discoveries with cautious wonder. Each object challenges existing models and forces reevaluation of long-held assumptions. The appearance of 3 confirmed interstellar objects within less than a decade suggests that the galaxy may be teeming with such wanderers. If so, the implications are enormous. The boundary between interstellar and interplanetary space becomes less distinct. Our solar system is not an isolated bubble, but a porous node in a vast, dynamic network of cosmic exchange. Material from distant stars drifts through ours, just as fragments from our own system will one day journey outward into others. The scientific pursuit of understanding 3I Atlas also connects to a broader question: what role do these objects play in the grand architecture of the universe? Some researchers propose that interstellar debris could act as seeds, transferring complex molecules between planetary systems, a process known as panspermia. Though still speculative, the idea carries weight in astrobiology. If 3I Atlas contains organic material that formed around another star, it demonstrates that the building blocks of life are not confined to a single planetary nursery. They are, perhaps, the universal language of creation, written into the dust and ice that wander the galaxy. But beneath the poetry lies rigorous science. Every observation requires calibration, every data point verification. NASA's analysts cross-check each signal against noise, each reading against known baselines. The 3I Atlas data are filtered through algorithms that remove the distortions of Earth's atmosphere, ensuring purity before interpretation. When anomalies appear, small shifts in brightness or velocity, they are logged meticulously. These variations can reveal rotation rates, internal structure, and even possible fragmentation. The process is tedious but vital, because every minute of observation brings humanity closer to understanding what interstellar space truly contains. The scientific context surrounding 3I Atlas, then, is one of both humility and ambition. Humanity stands at the edge of a cosmic shoreline, watching as fragments from other stars wash upon its sands. Each object, like 3I Atlas, reminds scientists that the universe is interconnected in ways still barely understood. The same forces that shaped Earth and its neighbors are at work across countless systems, scattering evidence of their processes like cosmic breadcrumbs. To study 3I Atlas is to study not just a single object, but the shared history of worlds unseen, and the mechanisms by which the universe continues its endless, silent dialogue across the stars in the realm of planetary defense and deep space observation. A quiet competition has always existed, a race not fought with weapons or borders, but with telescopes, algorithms, and time. The quiet race for detection is one of the most subtle, yet consequential rivalries in the modern scientific world. It is the race to see first, to know first, and to prepare first. While the public often associates space exploration with cooperation, the discovery and monitoring of near-Earth and interstellar objects have become fields where nations quietly measure each other's capabilities. Every detection, every reactivation of a system like NASA's 3I Atlas, every newly charted object from beyond our solar system represents more than scientific achievement. It represents a step in a global contest of awareness, precision, and control. The United States, through NASA, holds one of the largest and most advanced networks for tracking space objects, yet it is not alone in the pursuit. The European Space Agency, the Russian Federal Space Agency, China's National Space Administration, and several private and academic observatories have all developed programs dedicated to scanning the skies for potential threats and discoveries. Each system uses different methods, but the goal is the same: to identify cosmic bodies moving near Earth before they can pose a risk, and to catalog those that come from beyond. What makes this race quiet is not secrecy for its own sake, but the delicacy of information, because knowledge of what moves in the heavens can also translate into strategic advantage on Earth. The story of the 3I Atlas activation fits directly into this race. When NASA initiated the reactivation of its Atlas system, it wasn't merely responding to a single anomaly. It was reaffirming its role as the world's leading early warning authority for extraterrestrial events. For the United States, Maintaining this leadership is a matter of both scientific integrity and national security. The ability to detect and track fast-moving interstellar objects before anyone else ensures that data can be controlled, analyzed, and shared on American terms. Such information can shape international research priorities and influence funding and collaboration agreements across the globe. Even among friendly nations, there is competition to publish first, to model first, to confirm first. In scientific discovery, timing is everything. The race for detection operates on multiple fronts. The first front is technological. Telescopes are no longer just mirrors and lenses. They are integrated digital ecosystems that combine high-resolution optics with artificial intelligence and machine learning. NASA's Atlas system, for example, uses pattern recognition software that compares real-time sky data against massive catalogs of known objects. These systems can detect subtle motion or changes in brightness that human eyes would never catch. Meanwhile, China's Sky Survey Network and Europe's FlyEye telescope program have developed parallel systems with their own specialized methods for scanning the heavens. Each network refines its accuracy with every observation, learning from the faintest movements of light across the cosmos. The second front is data processing. Detection is only as good as the ability to interpret what is seen. Modern astronomy produces terabytes of data every night, and the true challenge lies in sifting through it to identify anomalies. In this domain, computing power is as important as optics. NASA's data analysis centers, supported by supercomputers capable of performing trillions of calculations per second, can model orbital paths, estimate mass and composition, and even simulate potential outcomes of close approaches. Other nations, recognizing the importance of these capabilities, are rapidly developing comparable infrastructure. The race is not only to see, but to understand faster and more completely. Yet despite the competition, there is an undercurrent of cooperation that threads through this global effort. The cosmos is vast, and even the most advanced system cannot cover it alone. International agreements allow for the sharing of limited observation data between major agencies. Still, within those exchanges, the subtext of rivalry remains. Each agency holds back certain information until its internal teams have verified or published it. In the world of space science, discovery equates to prestige, and prestige brings funding, influence, and technological leverage. The quiet race for detection is as much about identity as it is about protection. The race also extends beyond governments. Private companies and universities have become unexpected players in this unfolding competition. Advanced optical systems operated by private observatories, such as those funded by billionaires and research foundations, have begun contributing data rivaling that of national space programs. Their involvement has democratized detection while also complicating the secrecy once surrounding it. NASA, while remaining the global authority, must now coordinate with a web of independent observers who can identify anomalies in the same sky. The result is a paradoxical blend of transparency and control. The heavens are open for anyone to observe, yet interpretation remains guarded. As NASA reactivated 3I Atlas, the quiet race intensified. Rumors spread among the international astronomy community that something unusual had prompted the move. While NASA remained silent, observatories in Europe and Asia adjusted their own monitoring schedules, scanning similar regions of sky in an attempt to confirm what the Americans might have seen. This silent coordination, half cooperation, half competition, is a defining feature of modern space science. Nations may share the same sky, but they interpret its secrets through their own ambitions. Each wants to be the first to define a discovery, to own the narrative, to place its name beside the coordinates of a celestial traveler. The scientific reason behind this urgency lies in the rarity of such detections. Interstellar objects like 3I Atlas appear unexpectedly and vanish quickly, making every hour of observation precious. A few missed nights can mean the loss of critical data that can never be recovered. For scientists, this is the equivalent of watching a comet blaze across the sky only once in 1,000 generations. For governments, it's an opportunity to demonstrate capability, the ability to respond instantly, mobilize resources, and extract data before the object disappears into the cosmic dark. Beneath this scientific urgency lies another, quieter motivation. The detection of interstellar objects serves as a proxy for testing broader surveillance and monitoring capabilities. Systems that can track fast-moving celestial objects can also, in principle, track artificial one satellites, debris, or unidentified aerial phenomena. The same algorithms that analyze orbital paths for asteroids can analyze trajectories for objects within Earth's atmosphere or just beyond it. This overlap has turned the field of planetary defense into a domain with strategic significance, where the lines between astronomy, aerospace engineering, and defense technology blur. When NASA activated 3I Atlas, defense agencies around the world paid attention, not just because of what it might detect, but because of what the activation implied about American readiness and capability. In the quiet race for detection, speed and precision are the true currencies. The sooner an agency identifies an anomaly, the more control it has over the narrative and the data that follow. The discovery of 3I Atlas underscores this reality. The object was identified first through NASA's own network, and by the time other observatories confirmed it, NASA had already built a detailed model of its motion. That head start allowed American scientists to dictate the scientific framing of the discovery, ensuring that international studies referenced U.S. data as the standard. This influence extends beyond prestige. It shapes how future interstellar discoveries will be defined and categorized.